In this lesson, we're going to review loading diagrams and discuss how to calculate the stress, a stress state within a part. So far in this course, we've looked at stress states and looking at if there is an applied stress state, how to calculate what the principal stresses within that state are. We've looked at the relationship between stress and strain, and even very briefly mentioned that the strain, at some point in time, the stress will be great enough that the strain will be great enough that the part will break. So now we need to go back and fill in the details about how do we get this stress state anyway. So the first thing we need to do is to take a look at forces. So going back to static and dynamic force analysis. So the first thing we need to do is recall Newton's laws. So Newton's first law says a body at rest tends to stay at rest, and a body in motion tends to stay in motion unless acted on by an external force. Okay, so that's clear. Newton's third law says when two particles interact, a pair of equal and opposite reaction forces exist at their contact point. So that's also important, equal and opposite forces. The third one, which is the one that, or the second law, is the one that we need to focus in the most on, and it's a little bit more complicated. It says the time rate of change of momentum of a body is equal to the magnitude of the applied force and acts in the direction of that force. You know that probably more familiarly as F equals ma, although really maybe a better definition is that the change in momentum, the time rate of change of momentum, is equal to the magnitude of the applied force. So here's the time rate of change, and there's the magnitude of the applied force in the direction of that force. So let's break that down a little further. Oh, before we do that, recognize that G is the center of gravity, M is the moment, and H dot is the time rate of change of the angular momentum. Okay. So since the center of gravity plays into this equation, a lot of times it's convenient to go ahead and define a coordinate system that at least has its origin at the center of gravity. So its coordinate system runs through the center of gravity. So let's define a vector, a 3D vector. We'll call it R, and we'll say that R is defined by I, J, and K. Each of these are orthogonal to each other, and I represents the x-axis, and J represents the y-axis, and K represents the z-axis. And from there, we're going to say that sum of the forces in the x direction is equal to the mass times acceleration in the x direction. And in this course, we're going to consider mass to be constant throughout, so we won't deal with rockets that are burning up their fuel as they move. So with those assumptions and restrictions, these become pretty good working equations for us. The other set of working equations is to, again, going back to the actual definition, to Newton's second law, the actual definition. What you're probably most familiar with seeing looks something more like this, where the sum of the moments is equal to the inertia times the angular acceleration in that direction. A couple things we need to mention. There are other elements in this equation to be formally accurate. A lot of times in these problems in this semester, the angular velocity is going to be considered to be zero, so all of these terms will be able to cancel in the other directions. But this is the technical definition. And then let's go ahead and put the types of loading conditions into 4 different classes. So for instance, class 1 is constant loads, stationary elements. A bracket, you hang something on, it stays there forever. That would be a constant load and a stationary element. For class 2 load, this would be something like maybe a bridge. So we have stationary, here's a stationary object. The bridge is stationary, but as cars or trucks or whatever's driving across the bridge, the loads vary with respect to time. Then we have moving elements, constant loads. A drill press might fulfill this class 3. So the elements, maybe the tips of the drill bit as it's cutting into the material, are moving, but the load, the amount of material we're actually removing, is staying pretty constant throughout the operation. And then the most complicated case would be this class 4, where you have time-varying loads and moving elements, maybe a combustion engine. The elements inside a combustion engine, many of those parts will have time-varying loads and moving components. Okay. So for class 1, what we get to say now is that the sum of all of the forces are equal to 0. So it's far and away the most simple case, and it's what you did in your statics course. You made that assumption. And then we can, the other ones don't necessarily have the parts equal to 0. The sum of the forces don't necessarily equal 0, and we'll discuss those as we go along through the semester. The next topic we need to consider are free body diagrams. So let's just, the best way to introduce this is just to do an example. So here's an example of a crimper. A crimper is made up of, we'll say, 4 parts, where the 5th part is actually the thing that's being crimped. So you've got 2 handles, and then you've got 2 mechanisms working together to produce the crimping force. Okay? And the idea is we take some sort of crimping force that's desired, and we calculate the force of the hand. Now we're already seeing some assumptions jump in there. If I grab hold of a pair of crimping tool, I probably cannot apply an instantaneously, I can't apply a point load very well to exactly that location. But for the sake of analysis, and especially for the sake of building free body diagrams, let's assume that we can make this assumption fairly accurately. Okay? So what we're looking for is we're wanting to see how hard does a person have to squeeze in order to produce a 2,000-pound crimping force at that location. So the key to a free body diagram is to recognize each body has to be free. So for every independent moving body, it needs to have its own diagram. Now there's obviously a lot of repetition here, but of forces. So for instance, we know, because of Newton's laws, that this F3,4 will be equal to F4,3. But to set up the problem, we need to do it this way, and then we can begin making our assumptions and working on the geometry. Another first thing to notice is that we're going to put a center of gravity in each element. Each element has its own center of gravity, and each element has its own coordinate system that comes from that center of gravity. So now we have our R's calculated in terms of I, J, and K. In this problem, we're only really doing a 2D analysis, so we're going to say everything is happening when K equals 0, or when Z equals 0 in the K direction. Okay? And now, how many equations of motions do we have in this problem? So each body has 3 equations of motion. So F equals ma for each of the bodies. So that means there are a total of 12 equations that we have to govern. And this is again taking the understanding that we're in the plane. Okay, so we have movement. Each body can move in the x, it can move in the y, that's 2, and it can rotate about the z, that's our 3rd. So there's 3 equations of motion for each body, and there are 4 bodies, so there's a total of 12 equations of motion. Okay, so if we start looking at unknowns, we know F1c, we know that, and we know FC4. That both of those are equal to 2,000 pounds. That's given in the problem. The rest of the forces we don't know, and if you count them up, there are 17 unknowns. Now, some of these are repetitive. For instance, F4,3 and F3,4, I'm counting them twice. And then we also have, but we'll reduce those in just a minute. Okay. We also have some geometric constraints, and the geometric constraints give us exactly that relationship, that because geometry has to work, F4,1 has to be equal to F1,4. Okay? So we have 8 of those constraints, assuming that I looked through carefully. F4,3 is equal to minus F3,4. That's one of those equations. Okay? So we only need 17 equations. We have 12 plus 8 is a total of 12. There's a total of 20 equations. So we need 17 equations. We have 20, and we have 3. That means we have 3 redundant equations. Okay, so we'll have to get rid of those three redundant equations, and now we're set up. This becomes just a geometry problem, a basic statics problem. Given this force right here, and assuming statics, so assuming that we're not moving at this point, we could calculate all of these forces. Once we have these forces, now we have enough information to calculate this force. Using this force and a relationship right here, now we can calculate this force. And using all of that information together, we now can calculate this force and finally back out what FH actually is. Okay, so there's a quick reminder about what free body diagrams are. We also need to talk about beams. In this class, the definition of a beam is going to be that a beam is an element that carries load that's transverse to its long axis. Okay, so here are the four classic examples of beams. Example number A is simply supported beam. So you have two supports on either side, and you have some sort, and what's drawn in the picture is a distributed load along that acting down transverse to the long axis. The long axis in this case is on the x-axis. B is a cantilever beam with a point load. C is an overhung beam, has a moment loading as well as a linear distributed loading. And then finally, a statically indeterminate beam. We won't really talk about this until maybe a week from now, about how to calculate. What makes this problem difficult is since there are three reaction forces, it's no longer quite so simple to determine what the reaction load is. All of these other equations, given F, I can calculate R1 and M1 using the equations of motion, F equals ma, for this problem. Another concept we need to remember is what happens on the inside of a beam. So at the end of the day, what I care about is the stresses that are occurring within a part. And so to take a look at that, let's consider what would happen if we break this part into pieces. So what we're really going to do is make a free body diagram of part of the element. So let's say we break it maybe somewhere right in here. Okay, we're going to say the distance from the beginning is now considered x. So we're breaking it at x. And what we're going to say is that there exists some shear force at that location. And so what we're going to do is we're going to sum forces of, we're going to say, how does this have to be reacting so that this is static at that location? And we're going to see that there are definitely some forces occurring there, and there are some moments occurring there. So we're going to calculate what those are, and we're going to use that to figure out what the stress is at that location. It should make sense to you if you look at this total diagram that the maximum stress is not necessarily everywhere in this beam. Matter of fact, you can do a little bit of a thought experiment. If you've ever taken a long piece of maybe a 2x4 stretched across some cement blocks and you stood in the middle, you would expect that it's going to bend the most right here in the middle, and that if it were going to break, the place that it would most likely break would be right there in the middle of the beam. What we need to do is figure out mathematically why that's the case and figure out how to calculate that this stress will be higher than maybe a stress occurred here. And that's what we'll be doing as we move forward. Just a quick reminder about sign convention. Somebody decided this is what is considered positive shear and positive moment. Okay, and so that's what we'll use for the remainder of this class.